Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we are going to look at clustering methods. And here is the outline of the talk, and we'll start out with an overview and then step through each of the methods that are in Scikit-learn. We look at just the broad intuition and not any mathematical details of it. In this video, although we won't be covering the Birch method, we'll look into that in one of the future videos. And in the second half, we'll look at the different clustering performance evaluation methods that are available with Scikit-learn. And here is one reference. And this reference is for the affinity propagation. The real nice paper. I'd suggest you, if you have time, you could read this one. So there are a couple of terminologies. The first one is flat versus non-flat geometry. As we can see here in the picture on the left, we have this spiral arrangement of data points that could be considered as a non-flat geometry, where if we want to measure distance between this point and this point, we would be using something like a geodesic distance. And flat geometry would be something as shown on the right hand side, where we can use the Euclidean distance. Then there are two more terms, inductive versus transductive. And as shown in these flowcharts, transductive meaning the model that you create cannot be used on an unseen data for prediction, whereas inductive, you can use that model. So just these two terms, because now we'll be talking about them in this particular slide. So here, this is image from Scikit-learn docs, and it's really nice comparison. We have different clustering methods arranged here in columns, and each row is a different type of data arrangement or a data structure. And the first two rows are for non-flat geometry, as evidenced by these circles and curves. In and down here in the bottom, we have these three uh, types of data data sets which are slightly different. In this, the bottom case, this one, you can see that these blobs are about the same uh, spread. They have a similar spread, and so we could say they have equal variance within the data points or covariance between the data points. And these are elongated, and in this particular case, these data points are some are dense, but the shapes of them are different, so they are not the same shape as we see here. And here, this is another type of data set, as we can see. So in the table that's given in the docs, this is really nice comparison which tells when to use when is when to use which particular method. Uh, for flat geometries, so we have k-means right here and Gaussian mixtures. So that would be the first and last. So those would be for flat geometries. And then for non-flat geometries, um, most of the affinity, propagation, mean shift, spectral clustering, DBSCAN, optics. So those would be in the non-flat, which is these three right here, and then these two of DBSCAN and optics. Additionally, we can see the scalability for each of these methods. So for very large data sets, you could use the DBSCAN and optics. And also the Birch method is also suitable for very large data sets. And here we have the geometry, that is the type of metric used. Starting, there is Euclidean distance, Mahalanobis distance, and so on. Other methods are there. So this is a nice chart to come back and refer to when you're trying to work on clustering data set, until you get a feel for which method would be most suitable for the type of data that you have. Now let's begin looking at the clustering methods. The first one is k-means method. So here k stands for the number of clusters, and as shown here on the top right corner, we need to specify, we have to give this method how many clusters do we want it to find ahead of time. So let's say we have this particular data set. We see that this could be one cluster and this could be another cluster. So we give it two uh, two possible centroids or two starting points randomly in the space, and then the idea then is to assign the data points to each of these centroids that are closest. So let's say we assign the red ones to the red centroid and the blue ones to the blue one. So after this assignment is done, then what we want to do is uh, recalculate the centroid position based on the positions of these red for red and the blue for blue. So maybe this is the new set of centroids, and then again we assign the nearest data points to each of these centroids. So this could have been with red, but I just marked it as blue. So looks like it's more closer to red though. And finally, after a couple of iterations, we can arrive at a position where uh, the centroid doesn't move much, and that's when we know that the solution has converged. And thus we have these two clusters found. One is these red dots and the other is the blue dots. And this is the cost function that is minimized. So basically what we are trying to do is minimize the squared distances from points to their respective centroids using this distance. The mu is the mean right here. There is also k-means plus plus. So the difference being, in k-means we randomly initialize all the centroids in a single step, but in k-means that's not done. So what you do is randomly initialize just one centroid and then uh, pick another centroid based on probability values. So that's the difference. That's a way we suggestion discussion on that, but that's the main difference between k and k-means plus plus. So the this particular k-means plus plus, this way of assigning centroids apparently makes the algorithm faster. Next one is mini batch k-means. So as the name suggests, here the entire data set is not used as at once, but or picking batches from the dataset. So you have a dataset, you pick a batch, find the centroid, and then pick another batch, and then uh, update the centroid based on the new set of data points. Now, one point to note here. Here I've mentioned centroid, so this could be just one centroid, or it could be more centroids. Affinity propagation. So this is a different type of thinking in this particular algorithm. Uh, so in this case, there is word called exemplars. So exemplars, you can think of them as centroids. So the centers are selected from the actual data points, and then mm, the thinking is that the data points talk with each other, and they talk by uh, in terms of responsibilities and availabilities. So there is a responsibility matrix that is calculated, and there is an availability matrix that is calculated. So what the responsibility matrix tells is, let's say we have these three data points here, and we have this I data point right here, and we have this the red arrow going from I to K. K, let's say it's a exemplar, and this is RIK, denoting that the responsibility uh, R. So what we are trying to say here is how good is the point K to be an exemplar of point I. So that's what we are trying to find out. And then on the right hand side, we have the arrow switched around, and here what we are saying is that how appropriate would it be for point I to choose point K as its exemplar. So it's a two-way communication between each of the data points, one trying to see if it can be a centroid or exemplar, and the other point trying to see if it can be with that particular exemplar, or it needs to find any other another exemplar to be associated with as a data point in the cluster. So this, let's say we have these gray dots as data points. Initially, the availability is set to 0, and with each iterations, the metrics for availability and responsibility are updated, as shown here by the arrows. The arrows get darker in some cases, and the color of the dots also change. That is suggesting that as the iterations proceed, one of the data points is moving towards becoming an exemplar. So in this case, this particular data point, which is dark orange, becomes an exemplar uh, as and forms a cluster of these 3 points after converging. And the responsibility matrix for the sample K to be exemplar of I is calculated based on this relation, which is based on the similarity between the samples I and K. Again, on the right hand side, we have this AIK, that's the availability. So the availability of sample K to be exemplar of X is given by the minimum value of these two, either 0 or responsibility of K plus and the summed responsibilities of I dash K. And to these, in scikit-learn implementation, lambda term is added for both responsibilities and availabilities calculations, and that is to avoid numerical oscillations when the matrices are updated. That is to say, mm, when updating the messages. Next method is mean shift method, and in this method the data points are assumed to be sampled from a PDF or probability distribution function. So a very general intuition of this method would be like this. Let's say we have these data points, gray data points shown here. What we can do is uh, now here we are initializing with these 4 centers, so with the area region of interest around it, and with this the idea then is to find the mean shift vector to shift the center towards a higher density of data points, and this is the iterative process. So as we move through the data, finally we'll arrive at a position where the this particular center does not move much because it has reached the peak of the or it has reached the most densest part of the cluster. And in this case, as we go through, so this would be the final case, and here you can imagine that this is like a curve going up, down, and coming down here. So this would be the peak of a hill, and this could be the contour, which is here I'm showing just one, but if you draw more contours around this could be like the hilltops, 4 hilltops, and then valleys down here between them. And this is the mathematical equation for updating each of those candidates, which is these blue crosses shown there, by using the mean shift vector, and the mean shift vector is calculated by the relation here. is again based on the kernel xj minus xi. Next, for spectral clustering, here we need to specify the number of clusters to be found. So let's say we have this data set, then this data set on this data set, first a KNN graph is computed, then spectral embedding is used to project that into a low dimensional space, where afterwards a clustering method k-means can be used to find the clusters. So here are little detailed steps. Say we have our data which has 6 data points and the graph looks like this. So we have these circles could be called as nodes, and the lines between the circles could be called as edges. So each of these edges have weights 0.7, 0.9, etc. So the first part is then to find the adjacency matrix, which is shown here for this particular graph. Here we have uh, 1. So let's look at no 0.1. 1 connected to 1, so we put a 0 here. 1 connected with 2, we have 0.7, so we put a 0.7. 1 connected to 3 is 0.9, we put a 0.9. 1 connected to 4, 5, 6, no, so we just put zeros in there, and so on for the rest of the data points there. After we have the adjacency matrix, we can calculate the degree matrix, which is the row sum. So 0.7 plus 0.9 would be 1.6, and so we have 1.641. So we are adding the summed values only to the only to the diagonal of the matrix. For 5, here we have 0.7 plus 0.7, so 1.4, and so we have 1.4 here. After finding the degree matrix, we can calculate the Laplacian matrix by subtracting d minus a, and so we get this interesting matrix where uh, points to note are that the diagonal elements are positive and off diagonal elements are either negative or 0. And within the off diagonal elements, if it's a 0, then it means that those nodes are not connected. For example, 1 and 6 have a 0 here, so 1 is not connected to 6. Whereas if you look at 4 and 6, so 4 and 6 are connected, so we have a non-zero value there. Now, with this Laplacian, we can calculate the eigenvalues and eigenvectors for that matrix, and we get these set of eigenvalues right here. So the second largest eigenvalue, in this case 0.13, is called the connectivity, and the largest eigenvalue is called the spectral radius, in this case, which is 2.655. And this particular set of eigenvalues is called as a graph spectrum. Now, what we then want to do is pick the second uh, eigenvector based on this, because the second eigenvalue is better. The smaller the eigenvalue, the better it is for partitioning. So we pick the second vector and then use that to partition or cut the graph to create the cluster. So we can, for example, use this particular eigenvector to partition this graph shown by a dotted magenta line here. Next, we have hierarchical clustering. So hierarchical clustering, as you probably imagine, there's a tree involved here, and there is. So let's say we have these 16 data points, and if I ask you how many clusters you can see in these, so we can say there are 2 clusters shown here by dotted orange lines, or we can say there are 4 clusters as shown the dotted green lines, or we can go on and say 8 clusters, or if individual data point is a cluster by itself, then we have 16 clusters. So the idea then is to build a tree around each of these clusters and such that towards the bottom of the tree, the leaves where there are, we have a uh, finer sizes of clusters, and as we climb up the tree towards the root node, the clusters are much larger. So the method then is agglomerative clustering. So let's say we have these data points on the left hand side, and on the right hand side these arranged data points in a straight line. That's where we are going to build the tree. So the idea here is to connect neighboring data points and then draw a line on the right hand side. So first we connect 1 and 2, and so we draw a connection between 1 and 2, the height of which is representative of the length of uh, this particular distance between those 2 points. Next we connect 3 and 4, so that's what we do here, and so on. Then we connect. Now remember that now we have 1 and 2. After we connect them, it is now considered as a cluster. So when we are looking at 1 and 2, we are not looking at 1 and 2 as data point, where we are looking at it as a cluster of 2 points. So then we connect these two clusters uh, by this line, and so that becomes one large cluster, and we see the line here. Next we connect these two data points, they form two more clusters, and then those are connected to form much larger cluster, and then these two clusters can be connected, so we get this particular tree going on the right hand side, and then we find this cluster here, and finally collect all the clusters. So the top here, up top here in the root node, all we have is just a single cluster which has all data points. Then as we travel down through this tree, we get smaller and smaller clusters until the point we reach the very leaves of the tree where we have individual data points. Now in scikit-learn, there are different ways we can uh, create the links between data points and clusters, and these are listed here. There is ward, average, complete, and single. So ward, it minimizes the variance of the clusters that are being merged, then average uses average, complete or maximum uses the maximum distance, and single uses the minimum distances. Moving on, there's another interesting method called DBSCAN, density based spatial clustering of applications with noise, and this method works with irregular shaped clusters. So let's say we have a cluster shown by the gray data points on the left hand side. There are two important parameters that we can use to control the clustering in this method. The first one is radius, or radius of neighborhood, that is also called as epsilon, EPS, and the second is minimum of number of core points, or minimum number of data points that should be within that circle. So let's say we have uh, r is equal to 2 and m is equal to 5. So and we randomly pick one data point. So if we draw a circle around that data point with a radius 2, then what we want to do is count how many data points are within that circle. So we are looking for 5 points, and so here we have 5 points. So including the point in the center, so we can say that this particular point in magenta is a core data point. Next we move. What we then do is we go back. So we pick another data point from this circle and put it at the center of the circle, draw another circle. Let's say in this case we pick this data point right here, and if we make that as a center, we draw a circle and we count how many data points are within this circle. Again we see that we have 5 points, so we label this as again a core data point. core point, and then moving, we continue this process until we find until we traverse to the data set. And if we reach a position, whereas in this case where there are only 4 points in the circle, we need 5 to make this a core point. So this particular point is then called as a border point, and it's not a core point. And there could be some data points where there is only one data point in the circle around which it is drawn, so there are no additional points, and such a point could be called as an outlier. And so on, we complete moving through the entire data set. And then what we want to do is connect the neighboring centroids into the same cluster. So here we connect all these into one. This could be another by itself, and thus we can then call this as one cluster, because all these data points were associated with the 4 points in this cluster, and this was another cluster. Next is optics, which is ordering points to identify the clustering structure. So the authors of the DBSCAN, I believe, were the same team who who have developed this algorithm, which could be thought as generalization of DBSCAN, where in DBSCAN we need to specify the EPS epsilon or the value of r, that is the radius of the circle. However, in this particular case, there is no need to do that. And the advantage of that then is, let's say we have the clusters of varying density as shown here. This one is the densest, this is slightly less denser than this one, and this is very sparse. The data points are far apart, but still it's a cluster. So how does one work around such a data set? So here the idea is to find a reachability. Reachability is again a value that tells how dense the cluster is. So if we plot reachability versus the cluster order, then we can see these valleys and peaks. So the deeper the value, it tells that the reachability values are much smaller. That signifies that the clusters are much dense. That is, the distance between the data points within that cluster is very small. And if the uh, values are much shallower, as shown on the right here, it can tell us that the cluster, the data points in the cluster are spread far apart. And here is an actual example where we have these three clusters. So this is the densest one. This is more open, and this is in middle between those two. So here we can see that the height of the bars is much smaller in this particular area. That could be signifying that um, the reachability scores are small, and hence the data points are more tightly packed in that cluster as compared to this cluster where the bars are slightly higher, and on the right hand side these bars are much higher. The Birch method, I'm still trying to wrap my head around this particular method. So once I have this ready, I'll put this in a separate video.